Hello and welcome back to Calculus 3, section 11.8 on length of curves. We would like to figure out the distance traveled along a path. We said already that we had the lecture on motion in space previously, but we never talked about the distance, right? We said you can find the position. Position is a point in space. Position where you sit. That didn't cover the path it took for you to get to that seat, right? And that is the vector r. So now I have some kind of a vector r over here again, right, in time. And there is a position at t0, right? There is a position. I want to know the length of the curve. Length of the curve would be the distance traveled in space. So now what I can do is I can use the concept from Calculus 2 and upgrade that into our Calculus 3 formulas that we are going to need. So if you look at some kind of, so we're going now to, just briefly, jumping to 2D, we're going to have some kind of a function, and then we're going to have, for this function, we're going to have this delta x part, which we are observing with a delta y change, and then there will be this length here. It's not that this arc length here is not the same as the curved length, so we'll call this lowercase l. So if you solve for this lowercase l, l is equal to the square root of delta x squared plus delta y squared. You factor out delta x squared, so that's going to be delta x squared 1 plus delta y over delta x squared, and then you kick delta x outside, you get L equals delta x square root of 1 plus delta y over delta x squared. From there, right, this is the length of one line segment. You add all of the infinity of those, you would get that length of the curve L is given from A to B of 1 plus f prime of x squared dx. So this was your, good effort. This was your length of curve in 2D in rectangular coordinates. Now that's your Calculus 2. I believe this was a 6.5 or 6.6, probably 6.5 in your Calculus 1, Calculus 2. Now, what do we want to do here? We want to take a look at this and say, well, can I have this in terms of polar coordinates, and can I have this in terms of parametric equations? Because remember that R is given as a set of parametric equations. So it should be very useful to have the length of curves that involves the parametric equation set. So let's do that. So now let's take a look at the parametric form. Now, for the parametric form, what I'm going to do is I'm going to transform the problem that I have from before. So I'll say L integral a to b square root of 1 plus, and I'll leave this as dy dx. I use the Leibniz notation, dx. So what I'm going to do is I'm going to multiply this by dt over dt. So that's the way I fix this. So we know that parametric equations depend on the parameter t. So now that immediately brings this well, let's write it one more time. dy dx everything squared, and now I have dx dt times dt. So this, and t is between a and b, right? So now this t becomes the parameter, and then that you can think of time if you want to, and that's going to be between a and b on that time interval. So now this thing here needs to go under the square root, and things that go under the square root, they pick up a square. So this is integral a to b, square root of, I have 1 plus dy dx squared, everything times dx dt squared, and I have dt. So that's equal to a to b. And then when I multiply this, it will be dx dt squared plus, you see that dx squared and dx squared cancel, so it just becomes dy dt squared dt. For the formula, a to b square root of, and now you have your the derivative of x in respect to t, so we'll call that x prime of t plus squared plus y prime of t squared dt. So this is our R2, right, two-dimensional parametric form. R2 parametric form for length of curves. Now, if I want the 3D, well, you just toss in z inside. You know that's how you make your 3D equations. This is parametric, so you can just keep adding components. So length is, again, parameter a to b, x prime squared of t plus y prime squared of t plus z prime squared of t. dt would give us the 3D form, so this would be R3 parametric form. Now, as you are looking at these, right, hopefully you are noticing under the square root that you actually have the length of the vector, right? You have the length of the vector. That's just the magnitude. So I would like to write the length of curve in the most compact form that you can think of, and that would be a to b of the velocity, right, of the speed dt. So this is the Boss equation, actually. This is the Boss equation because you have we know that this thing over here is the speed. This is also speed in 2D. The one on the bottom is speed in 3D. So depending on what dimensionality you have of your vector. But this is the Boss equation here because this one is any dimension and any dimension space. So you just say, okay, whatever amount of components I have, whether it's a 2D or a 3D. So this is the general case. General case, i.e. any dimension, 2D, 3D, whatever. So now, when you are given, also, I'll just put here note that your velocity vector is given as r prime of t. So the honors option, this could be your question to derive parametric form on the exam. So far as you are preparing, well, right now it's just you, but if anyone else wants to prepare for the honors option, on the exam you have to all of those proofs for properties of vectors, you have the derivation for the length of curves from the Calc2 formula into the parametric form and also in the polar form. So all of those are on the pile.
If you're not being honest, you just simply memorize where this is.
That's what you simply are doing, yes. So now, given any r, you just compute r prime and you find its magnitude and you integrate that. That's very, very simple. Guys, length of curve, the answer should be 7 or 1/2, right? We're looking for length of curve. So that's, you know, how many feet you go forward or in whatever pattern you are going. That will be described by r. Let's take a look at an example. And then we have the polar form and we're done. So what do we have? Should we do Slinky again or do something else? Sick of Slinkies, right?
No, they are wonderful points.
Priceless. Yes. What kind of chemistry are you doing? What kind of chemistry is that? What kind of witchcraft is that? Let's see how bad problem 24 is. So we have problem 24. R of t is given as 5 cosine t squared, 5 sine t squared, and 12 t squared, and t is between 0 and 2. To find the length of the curve. So we have our r, so velocity vector v would be the derivative of this monstrosity here, so that's going to be 5 sine t, negative sine, right, and then 2t, so negative 10t sine t squared, 10t cosine t squared, and 24t. That's our velocity vector v. Now we need to find the magnitude of this, which will square all of these guys. I have a square root of 100t sine squared t squared plus 100, no, that's t squared, 100t squared cosine squared t squared, and plus 24 squared. What was the 24 squared? That is 376.
We're going to keep 576.
576. There we go. Good. So now we factor out 100t squared. You factor out 100t squared, sine plus cosine is equal to 1. So we have 100t squared times 1 plus 576t squared. That's going to give us t square root of 676. So that's our v. So now our length of curve is the integral 0 to 2 of square root 676t dt. Square root of 676 goes the outside. We have t squared over 2 from 0 to 2. And that's going to be 2 square root of 676. Yay.
Why, so question on the first part of it. When you square cosine t squared, wouldn't it be t to the 4th?
No. It's a sine. T squared is the argument of a sine. And now it's the time for us to build the last formula, which is the polar form. And we are done. So to build the polar form, we are going to start with our parametric form. So a to b square root of x prime, well, I'll put dx dt squared plus dy dt squared dt. And I'm just going to first start off with saying, since we are going into a polar form, I will change time with theta. So L is now going to be alpha to beta. Those are our limits because we are switching to theta domain. Square root of dx d theta squared plus dy d theta squared d theta. So all I did is I just swapped the variable parameter t for parameter theta. Doesn't matter. We can use whatever we want. Now, recall from your previous life that x is equal to r cosine theta and y equals r sine theta. And very important that r is the function of theta. So now, when you look at the formula and what you have to swap, you have dx d theta. Well, dx d theta, when I take the derivative, I have a product rule. So, x equals r cosine theta is actually f of theta cosine theta. And when I'm looking for dx d theta, that's a product rule. So copy the first times derivative of the second. It's going to be a negative in front. Plus copy the second cosine theta times the derivative of the first, which is f prime of theta. So dx d theta is given as, I'll write the derivative first. I have f prime theta cosine theta minus f of theta sine theta. This is our dx d theta. dy d theta is going to be f prime of theta sine theta plus f of theta cosine theta. That's our dy d theta. And now these two plug in L. So this is what we plug into the integral. So now we have L is equal to integral alpha to beta. And now we have a square root of the big one squared plus the other one squared d theta. 3 dots, sum algebra. Now you have to square, and then when you square, the stuff will simplify to get to alpha beta square root of f of theta plus f prime of theta, and those are squared, both d theta. So this long expression here, the blue star goes there, the green star goes in there, you square them, you will have 6 terms altogether when you square it out. The middle terms will cancel. You'll be able to pull the ones together, and this is what will survive at the end. All right, when you factor them out, sines and cosines will be 1. Sine squared plus cosine squared will be 1. So there are 3 lines of a lot of writing missing. And that's what we have. That's the derivation, and this is our polar form. Guys, polar coordinates 2D. There is no 3D equivalent over here. That's it. This is it, because this is only for length of polar curves, and polar curves are given as r theta for the points. That's the 2D surface. There is no 3D upgrade on this. So length of curve for polar coordinates can only be used for the 2D examples. Now let's take a look at the single example and then transition into your lab. I don't know, picking a random problem, 36, spiral. R equals 4 theta squared from 0 to 6. Well, your f of theta is given as 4 theta squared. Your f prime of theta is going to be 8 theta. And now you have to square both of these and plug them inside so we have 0 to 6 radians, square root of f squared is 16 theta to the 4th plus 64 theta squared, and then we have d theta. We can factor out 16 theta, so that's going to give us 0 to 6. When I factor out 16 theta, I get 4 theta outside of the square root. I get 1 plus 4 theta, no, theta squared, right? Mm-hmm. Theta squared plus 4. That's better, right? Mm-hmm. D theta. And what now? Thank you very much. So u equals theta squared plus 4. du equals 2 theta d theta. I have 4, so I have to kick 2 outside. So I have 2, and then I have integral of u du. When I plug in 0 into my limits, my new limits are 4 and 40. When I plug in, I don't want to go back to thetas, it's a definite integral, so we're done right away. 2 square root of u, that will be u to the 3 halves divided by the 3 halves from 4 to 40. That's 4/3 of 40 to the 3 halves minus 4 to the 3 halves. And we have 4/3. Now, square root of 4 is 2, so that's 2 root 10 raised to the 3 minus 8. And that's equal to some decimals over here. If you are interested, here, just do it. But that's the exact answer. Exact answer will be 4/3 or something along those lines. Actually, you can factor 8, because 2 cubed is 8, you can factor 8. This is equal to, factor 8, that's 32 over 3. And then you have root 10 cubed minus 1. That's better answer. That's it. Bye.